On behalf of the committee, welcome to the ARMA Seismicity webinar series. I'm Sean Maxwell. I'm a co-chair of the Induced Seismicity Technical Committee of ARMA. And today we're very excited. Professor David Eaton, University of Calgary, talking about aseismic fault creep, talking about some Western Canada hydraulic fracture induced sequences. So just before we get to Dave, a few kind of housekeeping we wanted to go through. So before we get into kind of details of the upcoming schedule and the context of the webinar itself, we'd like to spend a few minutes. We've asked Peter Smealy, who's the Executive Director of ARMA, to give a quick introduction to ARMA for those of you that may not be aware of ARMA and what it does. So with that, over to Peter.
Thank you, Sean. ARMA is the American Rock Mechanics Association, and it was established in 1995. It was an outgrowth of what some of you may remember as the U.S. National Committee for Rock Mechanics, which was a part of the National Academy of Sciences, Engineering, and Medicine. Its mission is really to advocate for all aspects of rock mechanics and rock engineering, primarily through our symposium, which unfortunately was canceled this year because of the virus. We comprise about 900 members. You can see the percentages there of where they come from. Our largest growing sector is really non-US, so we are the American Rock Mechanics Association, but in large part we're more and more international. We do have corporate members, student chapters. We have a program where we recognize distinguished individuals as ARMA fellows, and we have a future leaders program that identifies mid-career people starting out in the field. Our next symposium, which is the 55th, is a succession from when it was at the Academy of Sciences, is going to be in Houston at Woodlands next year. And we publish newsletters, issue awards, and importantly, we maintain the U.S. membership in the International Society for Rock Mechanics. In this webinar is part of the top committee you see there on induced seismicity. But in addition, we have 4 other committees that are taking their cues from both the Hydraulic Fracturing Committee and this committee in setting up their own webinars. So the others that we have are on tunneling and drilling mechanics, engineering, and we have one plan we're just starting to get underway on carbon sequestration. It's just in the talking stages right now. So that is a very brief overview of what ARMA is, and we will certainly welcome any and all members of would like to join. Thank you. Back to you, Sean.
Great. Thank you very much for that, Peter. So, as Peter mentioned, one of the efforts that ARMA does is through the technical committees, and I think a great effort ARMA is putting forward is webinar series that go beyond just the traditional ARMA membership. So we've established kind of an induced seismicity community where we're communicating around these webinars. So I think a good example of the type of service that ARMA provides. And personally, I'm very excited to, I just learned this morning that next year's ARMA symposium is going to be actually in the Woodlands. So literally my backyard. So looking forward to that. All right, so with that, I'm going to pass it over to Jens Lensny. Jens, introduce the upcoming schedule for our webinar series.
Hi, everyone. I'm Jens Lensny. I'm a Mendenhall Fellow at the U.S. Geological Survey, and I'm very excited to show some of the talks, upcoming speakers coming up. We have a great schedule. Of course, today we have Dave Eaton from the University of Calgary, as we'll see. For those of you who were here 2 weeks ago, you saw the first few of these people on the list. James Verdon from the University of Bristol, we'll be speaking about the induced seismicity associated with hydraulic fracturing at Lancashire, England. After that, 2 weeks later, Ji Zhang will be speaking about induced seismicity due to shale gas production in the Sichuan Basin in China. About 2 weeks following that one, note the slightly different day due to the holidays. The 2nd of July at 10 Central, Stu Venables from the BC Oil and Gas Commission will be talking about the BC regulatory approach and some case studies there. And a new one on the schedule here is Elizabeth Cochran from the USGS, who will be talking about the clustering behavior of induced seismicity and implications for triggering processes with a special focus on southern Kansas and Oklahoma. So that's the latest one. These, as you can see, they come about every 2 weeks, except for the case of Stu Venables, which is 1 day off. And we'll be sending reminders about these periodically. Thanks.
Thanks, Jens. And over to Madi for a few more comments before we get started here.
Good morning, everybody. This is Mahdi from the Bureau of Economic Geology at the University of Texas at Austin. So first of all, it is our great honor to have so many people in this webinar. So far, we have around 70 people, but around 283 people have registered with us for the distribution. We have 127 people from the industry, or 45% of the community is from industry. From academia, we have 134 people, or 48%, and from regulatory agencies, we have 25 people, or 7%. So we have a good mix of industry and academia, and it's great to have this great combination of people from different sectors of induced seismicity, research, and operation. Next slide. So in order to have a better webinar for all of us, we have some simple instructions. So there is no need to subscribe for each webinar. So right now that you are in this webinar, it means that you will receive the emails for the upcoming webinars, unless you just let us know to be removed from the distribution list. So we ask you not to forward the webinar invites. Instead, please forward interesting parties to the community to be added to the distribution. We would like to grow this community and have a better connection in this time of the pandemic outbreak. Everyone will be muted during the talk in order to have a better recording quality and no distraction for the speaker. Please submit your questions during or after the talk in the chat button at the bottom of the Zoom meeting window. And please send these questions to everyone, because the organizing committee would like to summarize these questions in case they are very repetitive or they are very long. This Zoom meeting is recorded, and the link to the recording will be shared only to the participants after the webinar. And without further delay, let's invite David to have the presentation. Thank you so much.
Thank you for that introduction. I hope everyone can see the opening slide well enough. It's a great pleasure to be part of this series of presentations. I'm very excited. There have been some great presentations already, and I'm excited to see some of the ones that are forthcoming. You can see from the title here that what I'm going to be presenting today focuses on hydraulic fracturing induced seismicity, and some of our new models, which include aseismic fault creep mechanisms. The topics I'll be presenting are mainly observational rather than mathematical, but a lot of the underlying mathematical models you can get from the references that I'll be citing throughout this. I would like to just note contributors to this presentation, which include students and postdocs in my research group, as well as Mirko Vanderbaan, who's a longtime collaborator from the University of Alberta. This work is part of the Microseismic Industry Consortium, and we've received funding from agencies in Canada, including NSERC and the Canada First Research Excellence Fund. So given the theme of the series, I thought it would be great to start with kind of a global overview of hydraulic fracturing-induced seismicity. This is taken from a paper which has just recently been published with Nature. What you're looking at are hydraulic fracturing-induced earthquakes, as long as a number of earthquakes from saltwater disposal and enhanced geothermal systems. Of course, there are a number of very well-studied hydraulic fracturing-induced events in Western Canada, and that's going to be the focus of this presentation. But there are also well-documented cases in Oklahoma, Texas, Ohio, and we'll be hearing about some of the other ones, including induced earthquakes in the UK, and importantly, the largest ones recorded so far in the Sichuan Basin in China. Now, I had an animation that went with this slide, but when we tested this yesterday, the animation killed the Wi-Fi bandwidth with my home Wi-Fi. So I'm just going to show you one of the frames from it, but I think it makes the point that Western Canada is an excellent place to study this problem because it's such a data-rich area. The map that's shown in the middle of this shows data that we've compiled through databases provided by geologic systems. It covers British Columbia, Alberta, parts of Saskatchewan. You can see hydraulically fractured wells in here, color-coded by the specific play that's involved. There's also induced earthquakes that are shown on here. And as the animation plays, you can see these earthquakes occurring and regulatory responses. So, for example, the red boxes that are shown in here represent areas that where regulators have induced some special requirements for induced seismicity monitoring. And that includes areas within the Montney play in northeastern British Columbia, as well as the Duvernay play in Alberta. And in the top left, you can see a graph just showing the maximum magnitude of event which has occurred in each one of these squares, as well as the total injected volume, summing together all of the hydraulic fracturing operations within each square. And by and large, it seems to follow pretty well the well-known McGarr relationship, which assigns a moment cap to the maximum magnitude. But at a given instance in time, we do see events that pop up above it. I'll note that there's one outlier here, which is a natural event, magnitude 5.4 earthquake in April 2001. So it's unrelated to the induced seismicity story here. I'm just going to set the stage a little bit by making a few broad generalizations about comparing hydraulic fracturing induced seismicity with saltwater disposal. One thing to note is it's often considered that the injected volumes from hydraulic fracturing are relatively small compared to high rate injectors for saltwater disposal. But if you actually sum the volume from a kind of a typical multi-well hydraulic fracturing pad over the course of weeks and months, this ends up being, roughly speaking, about the same net injected volume as you might expect to see in a high rate injector over a year. In the case of hydraulic fracturing and induced seismicity, the events often nucleate within the sedimentary layers, so above the basement, whereas for saltwater disposal, generally the events occur within the underlying Precambrian basement. For hydraulic fracturing induced seismicity, it's usually not as difficult to attribute an event to a specific operation, so a pad, well, or even a stage completion. Whereas in the case of saltwater disposal, these events represent a combined effect of multiple sources. So trying to pinpoint an exact cause is a little more complicated. There is sometimes a difference in terms of the sequence of activities. So some people talk about swarminess of sequences from hydraulic fracturing. Here's an example from work done in Ohio, where you can sort of appreciate the swarmy behavior which is taking place. Whereas saltwater disposal induced earthquake sequences tend to follow a more typical main shock, aftershock type of sequence. And finally, in Western Canada, and some of the examples I'll be showing you today, hydraulic fracturing induced earthquakes tend to nucleate at some distance away from the injection sites, and distances in fact up to 2 kilometers, and with a temporal latency of hours to weeks. So after the injection itself. And these are all sort of parts of the clues and some of the perplexing observations that we've seen. So I'll talk a little bit in this presentation about underlying physics and what we think are activation mechanisms. This picks up on some of the themes that we heard about in the previous presentation by Mark Zobak, where we're interested in really trying to understand some of the physical mechanisms. Broadly speaking, I'm classifying them here into 3 categories. So classically, there is a direct pore pressure effect from hydraulic fracturing. And in this diagram, I've also included saltwater disposal, but I'll be focusing on hydraulic fracturing. And you can see I've sketched a fault which extends down into the basement and includes, in some cases, these kind of flower structure features in the sediments. Another broad category, change in fault loading conditions. And finally, the aseismic creep. And I'm going to sort of dive into each one of these in a little bit of detail in the next couple of slides. So in terms of the direct pore pressure effect, the creation of hydraulic fractures results in tensile fractures with high fluid pressure inside the fractures. There is usually some leak off into the formation as depicted here. What's shown here with the fault is we also have kind of a damage zone shown schematically around the fault where we would expect there to be fractures and possibly higher permeability. So a hydraulic fracture that intersects the fault damage zone or even the fault itself would of course be expected to increase the pore pressure in the fault core, and that could directly lead to frictional instability in the fault as a result of the increasing pore pressure. And here's just an example of some calculations that really illustrate this type of phenomenon. A lot of papers on hydraulic fracturing induced seismicity look at other possible mechanisms, sort of broadly labeled here as a change in fault loading conditions. So for example, Deng et al. Looked at a sequence of earthquakes in Alberta and the Duvernay play in 2013 and did a fully coupled poroelastic simulation to try to understand the Coulomb stress changes that would be expected to occur purely due to poroelastic coupling between elevated fluid pressure and stress changes around the hydraulic fracture and the surrounding medium. And they showed that most of the induced events fell within an area of positive Coulomb stress change, shown here in red. But the magnitude of this is fairly weak. So they're seeing about 0.02 megapascals of change as a result of poroelastic changes. Catleti et al. From the Bristol group have also considered the direct elastostatic effects of hydraulic fracturing and the combined effects of clusters of induced seismicity. So hydraulic fractures, of course, strongly perturb the stress state in the vicinity of the hydraulic fracture, and that itself could play a role if the fracture intersects into the fault zone. So in this paper, they're finding somewhat larger stress perturbations that they could attribute, especially when they considered clusters of seismicity. So one of the things I'm going to be developing in this presentation using a case study from Alberta is the possibility that one of the main primary causative mechanisms is that hydraulic fracturing is driving a slow slip process at the depth of the hydraulic fracturing, but the slow slip on a fault is loading other parts of a fault, which could then indirectly lead to some kind of delayed dynamic rupture. That's indicated in the schematic on the right. In this schematic, we're showing the seismicity occurring actually above the treatment zone. It could, of course, happen either above or below, but in the particular example that we studied, and this was published in Science Advances last year, the activity took place above the injection zone, and that was actually one of the things that really sort of captured our interest and made us look into this in more detail. So this is the event that I'll talk about over the next few slides. It's a moment magnitude 4.1 earthquake. It took place in January of 2016 during a hydraulic fracturing program. It's in the vicinity of Crooked Lake, which is where the Deng et al. Poroelastic modeling work was done, but this was 3 years later. So the seismicity that was associated with this event was recorded using a dense array of buried geophones, and you can see in the map the distribution of these systems. So each one of these symbols represents a shallow well bore drilled to about 27 meters depth. And there's geophones that are cemented into the well bore, including a 3-component geophone at 27 meters depth. So this type of system is extremely effective at recording microseismicity, and we use this to look at the microseismicity leading up to the magnitude 4.1 event. So in this diagram, you can see on the left side in map view microseismic events. So here is the well bore. It was drilled. This is the horizontal well that was completed, starting in the south and working northwards. So each of these triangle symbols is showing a perforation, so for each of the individual stages. And these are color-coded by time. So this is time in hours working the way along the well. And microseismic events, which are shown on here, are similarly color-coded. And just glancing at this in map view, if you're used to looking at microseismic plots from hydraulic fracturing, it already looks really unusual because of the asymmetry. So almost all of the events are occur on one side of this hydraulically fractured well. They're also, even from the very beginning, oblique to the maximum horizontal stress direction. So we would expect to see symmetrical distribution of events either side of the well parallel to SH max. That's not what we're seeing. And as the completion progressed, these tended to rotate more and more into a north-south orientation. And finally, during the completion of this stage here, stage 27, a magnitude 4.1 event occurred on a strike slip fault just to the east of the wellbore. You can see all of this in cross-section on the right. And what's really unusual about this as well is that very little of the microseismicity occurred in the Duvernay zone for the completion. Some of it occurred below, but most of the microseismic activity, precursory activity, took place above the wellbore. And one might think that there could be some velocity model issues, and this is an artifact. But in fact, this is a very well-calibrated velocity model because all of the perforations were well recorded, used to calibrate the model, and so the perforations the perforation events locate along the wellbore, and these ones are confidently assigned locations above the wellbore. And the magnitude 4.1 event itself occurred several hundred meters above the wellbore, still at a depth of 3 kilometers below surface, but inside a formation called the Wabamun Formation, which is a massive carbonate unit, which forms some of the spectacular cliffs that you see in the Canadian Rocky Mountains to the west. So this really got our interest in trying to understand, because the expectation at that point in time was that most of the larger events would be expected to occur in the Precambrian basement. And we're not seeing a direct pathway that's connecting the hydraulic fracturing microseismicity up into that event. Well, one of the papers that influenced our thinking was this paper in Science by Guglielmi and others, published in 2015. And in this study, they used the SIMFIP downhole probe to investigate. So there was a hole that was drilled through an inactive fault within carbonate rocks. They packed off the fault, pressurized it, and then measured very precisely the dilation of the fault as well as the shear slip along the fault. And the conclusions from this work was that the fault slip that was induced through this injection program was mainly aseismic. So there was, in addition to fault dilation, they observed slow creep from 4 to 10 micrometers per second along the fault. There was a microseismic network that was being used concurrently, and they found microearthquakes that took place indirectly as part of this aseismic creep. So to really understand the potential for aseismic creep in these kinds of systems, I just want to talk a little bit about rate state friction models. And you can see in this schematic illustration some of the key features of this. This is a schematic, but it's well established from hundreds of laboratory experiments. So if you imagine you have a slip surface where sliding is occurring at a velocity v1, and then the sliding velocity is suddenly increased to v2, and we measure the friction coefficient mu during this experiment, then what's observed is an immediate increase in the friction coefficient by an amount A, followed by a relaxation in friction to a new steady state friction value. There's a parameter B in the rate state friction models, which determines how far that relaxation process goes down to. So if these parameters A minus B, or if the difference between A and B is less than 0, this leads to a velocity weakening or a rate weakening situation in which the new steady state friction is lower than the friction level at velocity v1. So you can imagine how this could compound into a feedback process that produces dynamic rupture. So as you increase the velocity, it decreases the friction and so on. So this leads to unstable sliding. You can get stable sliding in the opposite scenario where A minus B is greater than 0. So this new steady state friction is greater than it was before. And so this leads to kind of a maximum slip velocity and slow creep on faults. So this is some work that was done by the Stanford group, Coley and Zobak, published in 2013. This is based on measurements from a number of shale plays in the US. And what the graph is showing along the horizontal axis is measured clay plus total organic carbon in weight percent. This is versus friction coefficient as well as the A minus B difference. And what's interesting about this is once we exceed a certain level of clay plus TOC, according to these experiments, then we expect to get into a regime where A minus B is positive. So we would expect to get stable sliding to occur. And this is the regime where many of the shale plays exist in terms of the composition of the rock. So if we extrapolate from this, we would expect completion programs, if there are faults nearby, they might be expected to produce stable sliding, so aseismic creep rather than dynamic rupture. So we went back and revisited the January 2016 event, and what you're looking at here is a seismic profile extracted from a 3D seismic data set. It's perpendicular to the north-south well, so here is the location of the well within the Duvernay formation, and the red star is showing the hypocenter of the magnitude 4.1 event. There are a number of mapped faults in this area, but their seismic expression is remarkably subtle. But the faults are thought to extend through, and these are strike-slip faults, and they extend through the Duvernay zone up into the Wabman. You can see on the right, here's a histogram of the event count versus depth. And the peak in the event count occurs at the boundary between the Ireton Shale Formation, which overlies the Duvernay, and the Wobman Formation, which is a very thick, competent carbonate unit. And the event itself took place up here. And beside this, we can see a graph of clay plus total organic content weight percent. This is based on a suite of well logs, which were calibrated using core data from a nearby core where a full rock eval analysis had been done. And so what we find is below this depth, we see clay plus TOC content, which would be indicative of likely aseismic slip. And then above this depth, we see the opposite. So we see clay plus TOC negligible, which we might expect to lead to unstable sliding. So we teamed up with Dimitri Garagash at Dalhousie University, who did generated some numerical models to try to simulate this event. So what you can see on the top left is a diagram showing the pore overpressure that was calculated with 4 hydraulic fracturing stages, which are shown here. And on the right, you can see slip along a modeled fault. So the axis here is in meters, so it's up to 25 centimeters of slip. And because this is a rate state model, there was an initial very slow slip velocity along the fault. And that's represented here as geologic slip rate every 10 million years. So this dates back to about 55 million years ago, which was the time of peak hydrocarbon generation in the Duvernay Formation and maximum burial depth. So we have this very slow slip, which is occurring geologically. This is rapidly accelerated during hydraulic fracturing. So there are contours every 5.5 hours during hydraulic fracturing, which are shown as gray contours. And they contribute a few centimeters of displacement on this fault. In the last few stages, we get this aseismic creep, which is propagating higher and higher up along the fault. And the earthquake itself nucleated in this model in the Wobman unit and produced about 17 centimeters of total slip. So here, these are coseismic slip contours every 0.01 seconds. Now, one thing that was interesting about this work is that the initial models computed the magnitude of the event. So Dimitri was finding he was getting calculated magnitudes of about 3.4, but then he incorporated some laboratory measurements for flash heating in carbonates, which produce, with this kind of carbonate fault gouge, produces a sudden dramatic loss in mechanical strength. And once that was incorporated into the calculations, it agreed quite nicely with the moment magnitude of the event. So that kind of prompted us to develop this model for aseismic creep along the fault. This graph and the slide that you're looking at right now looks at the aftermath of the event. So continued monitoring and evidence here for a very persistent, prolonged swarm of events within the region. And this swarm of events is effectively stationary near the epicenter of the original event. So if you look at the graph, what we see here is an initial set of events that seem to follow an Amori decay pattern, but these then transition into a steady state linear trend of seismicity. And this continued for nearly 150 days. So the well was shut in. There was a traffic light protocol at the time. So immediately following the event, the well was shut in. There were discussions between the operator of the well and the regulator in Alberta. Permission was granted to flow the well back, but there was an aborted flowback attempt that only lasted a couple of hours. During that time, there was another magnitude 2 event, so there was another pause, and then flow back again. And this ultimately resulted in a reduced but continuing ongoing seismicity at a linear rate that you can see here. And there's a lot of interesting features. So we can see here a delayed Omori trend from the aborted flowback, and then another delayed Omori aftershock trend coming from the actual flowback. And so what this is telling us is that the well itself is still in some kind of stress or hydrologic contact with the seismogenic region, but that there's a few days delay in the communication between the well and the seismogenic region. So we've got a paper which is coming out which looks at this based on rate state type of analysis. So for example, I won't go into the details here, but using this Dietrich model for rate state friction, you expect that there's a steady state seismicity rate which is given by the ratio between the stressing rate to the background stressing rate. So what this appears to indicate is that there is a new stressing rate in this area. And in this paper, we argue that this ongoing stress rate and the stationary seismicity is best explained by the aseismic creep model, which we had developed earlier. So I want to just touch on another aspect of this work, which does not relate to aseismic creep. This is coming from a field program called the Tony Creek Dual Microseismic Experiment. This was collected in 2016 by the University of Calgary. It was to record a 4-well completion program in the same general area as the previous one that we were looking at. So here, once again, we have a set of, in addition to broadband seismometers and a strong motion accelerometer, we have a set of these shallow wellbore geophones with the deepest 3-component geophone at 27 meters depth and cemented into the hole. So again, a very good type of configuration to record microseismicity. I wanted to be sure to mention this because the raw data from this program has been provided to IRIS and will be publicly available starting on July 1st. So other research groups that are interested in trying to use this data set can access the data from IRIS. And there'll be a GitHub site which is going to be live soon, which will list publications to cite as well as catalogs. And that will include a catalog which was produced by Nadine Agonin, one of my PhD students who at the time was visiting the University of Bristol and using some of their codes. So this catalog has 18,000 events and really nicely illustrates, some of the features. So the largest events occurred again on a north-south oriented strike slip fault structure. So this is about 1.5 kilometers long. There was a number of other seismicity clusters that were observed during this program. The current model is that these wells actually sit within a flower structure with a underlying master fault in the Precambrian basement. And we might be seeing some Rydell shear structures with some bounding strike slip faults that you can see over here. Again, I had an animation for this, but I didn't want to tempt fate with my internet connection. But some of the frames from this animation are shown here. So here you see the 4 wells. This is the first well which was being completed using a kind of an unusual coil tubing method that had lots of individual fracture stages. The dashed lines are showing the regional SH max orientation. So that's the orientation we would expect for the microseismicity clusters. So this green ellipse is showing the expected orientation as well as extent of microseismicity in the zone. And then the red dots are showing microseismic events that occurred during the completion of this particular stage. So here's another snapshot. This is 48 hours later. And this is just when we started to see seismic activity occurring on this, this north-south fault. And to the right of that, you can see depth constraints that we have available. So we've developed some new methods for trying to accurately calibrate depth of these events, and these take advantage of 3D seismic data as well as 3D converted wave seismic data. What the depth constraints show us is that all of the events that are shown in pink appear to be occurring above the reservoir. So much as we saw in the previous example, the ones that are shown in black along here are occurring within the reservoir. So we think that these structures here are fracture systems located in the Ireton formation above the Duvernay formation, possibly Rydell shear structures. And if we take this orientation that we see here and extrapolate it along strike as shown with the green dash line, then it lines up with the onset of seismicity with about a 48-hour time lag. So this is one of 4 examples where we can see this behavior that's occurring on here. What Nadine and co-workers did was to model this scenario, making the assumption that these fracture systems, these putative fracture systems within the Ireton formation were more permeable. What this allowed to happen was a pressure pulse from the hydraulic fracturing to diffuse along the fracture network and ultimately reach the this north-south strike-slip fault. You can see the way the model was set up in terms of the dimensions of the fracture zone. Using this model, they tried a series of different possible permeabilities within the fracture zone and concluded that this range of permeabilities from 150 to 230 millidarcies gave a good kinematic fit between the timing of the hydraulic fracturing and the timing of the onset of seismicity along the fault. I just want to finish off very quickly with one other item that we're really quite interested in here, and that is the casing deformation, which has been documented in a number of areas, and in some cases areas where induced seismicity is known to occur, but to my knowledge at least, there is as yet no direct connection that's been made between a specific induced event and a casing deformation such as what you're seeing here. This particular example is from the Montney play in northeastern British Columbia. And there's quite a number of these examples which seem to exhibit casing shear taking place along bedding surfaces, which we know from geomechanical measurements are relatively weak surfaces in this system. And just to sort of make the general point, this is taken from a paper by Maurice Dussault, which talks about more holistically within these systems, connections between faults, reservoir compaction processes, and these kind of slipping surfaces which could impact casing deformation. So we're developing models right now where these connections are made explicitly, and we try to understand whether aseismic slip processes that are occurring on faults might be in some way related to slow casing deformation, such as what's depicted over here on the right. So I'll wrap things up there, just a few key takeaway points, and then I'd be happy to take any questions through the chat function. So first one, there are similarities as well as differences in induced seismicity behavior for hydraulic fracturing versus saltwater disposal. And both the similarities and the differences may be key to understanding the underlying physical fault activation mechanism. The broad categories for activation mechanisms within hydraulic fracturing include direct pore pressure effect, changes in fault loading conditions, so these could be through poroelastic coupling or elastostatic effects, and then this latest model that we're working on right now, which is aseismic creep. The aseismic creep itself could be initiated through a direct pore pressure effect or change in fault loading conditions, but this contributes to loading of an unstable part of the fault. I talked about this case study where the timing and relatively shallow depth of a magnitude 4.1 event can be modeled as fault loading through hydraulic fracturing accelerated aseismic creep on the fault. In the aftermath of that event, a subsequent swarm-like seismicity persisted for at least 250 days. So that's 250 days was the end of our study period, and it was still going. So this implies there must be some mechanism to maintain a constant stressing rate in the seismogenic area. And so we're appealing to this aseismic creep within the regional stress field as a possible way that we could achieve that. A lot of the work that we're doing right now in Western Canada seems to point toward the existence of permeable pathways. So the zones which are completed are themselves have a very low matrix permeability, and it appears that permeable pathways through fracture systems could play a really important role in connecting up fault networks with the hydraulic fracturing programs. And these can explain both the offset away from the hydraulic fracturing of 1 to 2 kilometers, as well as the latency that we're observing, the time lag between the hydraulic fracturing and the induced events. So that concludes my presentation, and I would be happy to take any questions right now. I can't actually see the chat function myself right now, so I'll rely on Sean or Maddie to sort of summarize or read out any questions that are showing up there.
Yeah, we'll help you out, Dave. So first of all, thank you very much for the very interesting presentation. That was great. And while people are contemplating and writing down questions, there's a few already on chat, but I think I'll kick it off with invoking executive privilege and ask the first question myself. I'm curious if you've given any thought as a mitigation strategy, is there any way we could somehow change operation to try to move more of the deformation to be aseismic as opposed to seismic release of the deformation?
Yeah, that's a really interesting question. And I guess in principle, if more of the deformation occurred aseismically, so for relieving stress on faults without producing dynamic rupture, then it becomes a more controlled kind of a process, which would be really interesting. And one of our kind of working models is that, in fact, the aseismic processes might be much more common than we think. So it could be that the induced events are the exception and the aseismic slip is the rule in working in these areas. And we're in the process of gathering some data to try to test that, that hypothesis. Possibly as we get that kind of data, it might help us to determine, whether that can be controlled, so whether there are any operational controls that might determine, if and when, aseismic slip then turns into a, dynamic rupture on some unstable part of the fault.
Great. Thanks for that, Dave. So there's a couple questions related to slide 15. So if you wouldn't mind, might be easiest if you go back to.
Okay, just give me a second. Okay.
So the first one is from Fushan Liu, who's asking, where are the induced seismicity event nucleated in terms of the dynamic rupture relative to this model?
So within this model, the hypocenter, the calculated hypocenter is, and I'm not sure if you can see my pointer very well, so I'm going to switch to a laser pointer. The calculated hypocenter was a few hundred meters above the well within the carbonate unit. So this is the Wobman carbonate. So the nucleation occurred up here. And in this model, the nucleation occurs when the creep front propagates far enough up into the Wobman. So this is a critically stressed section of the fault. It also has a rate weakening rheology. So once slip is initiated in here, we get this dynamic rupture process that produces the induced event.
Interesting. And then also Ellen Galloway is asking a question about the same slide. So the rupture model appears to constrain fault movement to 0 in the basement. Does that have any impact?
Well, certainly the seismic moment depends on the fault rupture area. And if our model is correct, and if the dynamic rupture is more or less constrained to this, this carbonate unit, then there's and we actually think that the top of the fault extends no farther than the top of the Wobman. And that's determined based on sort of geological reasoning on the youngest reactivation of this feature in the Devonian. So if the fault area is constrained by the thickness of the Wobman unit, then it would, based on, seismological principles, it would stand to reason that that would constrain the maximum magnitude of the event. So we can get, this is a strike slip type of earthquake. So the aspect ratio might be quite elongate, but certainly the height of the fault would be a factor. If this rupture extended down into Precambrian basement, so the crystalline basement is about 400 meters below the well here, then potentially, that would enable a much larger fault area to be accessed. So this event that we looked at here, based on aftershocks, has a lateral extent of a little over 1 kilometer. The Wobman unit here is about 300 meters thick altogether. So that gives you a sense of the fault rupture area. And this produced a moment magnitude 4.1 event. I hope that answers the question.
So thanks, Dave. Then I'm going to maybe pick on a couple of shorter questions that are easier to convey here. So Tony Kraft is asking if you've looked at repeating events as a way to try to confirm the aseismic creep hypothesis.
Well, we are using template matching as one of the primary methods that we're using to build these catalogs. So if I go to the this slide here, so template matching was used to obtain the aftershock swarm catalog that you're looking at here. And what was found is that most of these events are close to being repeating events. So we're seeing a very small mappable migration, but the migration is slow and it's quite constrained. It seems to be moving laterally along the fault, but only over a period of many months here, 100 meters or so along the fault. So I'm not sure about the semantics, whether these are exactly repeating events or not. But they're events that are occurring within a very constrained, localized area on the fault and have a very similar signature in terms of the waveforms that we're recording.
Great. And then I guess moving on, James Verdon's asking if it's really aseismic versus seismic slip, but could there be small events too small to be detected associated with the aseismic part?
Yeah, so if I sort of flip back to this slide, so what you're looking at here is microseismicity recorded using the 98 station shallow wellbore array, and this gives us, our best available resolution in terms of detection threshold for events. So this system has a threshold of about magnitude -2 or so. So here is the where that the magnitude 4.1 event nucleated. We're seeing a lot of seismicity below that. So again, this seismicity is kind of at the boundary between the Ireton shale formation and the overlying the Wobman. And there is this seismic activity which occurred just to the south of it along here, but about the same depth level. But based on our magnitude -2 detection threshold, we're not actually seeing a lot of small events as precursors to this. So you could think of this maybe something like acoustic emissions in the laboratory. Based on the available data, it looks to us as though true aseismic creep best describes what we're seeing. And then I guess going to the aftershocks, we have this issue of trying to explain, nearly a year's worth of ongoing activity on this fault. So we don't think you can explain it all with pore pressure. And so we're arguing here that there is a continuing aseismic creep process. And this is actually observed in a lot of natural swarm activities as well. So there's kind of a fluids versus aseismic creep explanations for these natural swarms. So the preponderance of evidence, I think seems to support this aseismic creep process is occurring.
Great. Thanks for that. And then I guess finally, I don't think it's really a question so much as kind of a virtual thumbs up from Mark Zobak, who I think is pleased that you're thinking along similar lines that he is of these potential permeable pathways as transmitting pressure and able to transmit significant pressure over distances. And I think there's several cases where maybe that's evident as a triggering mechanism. So I guess with that, there's a few other kind of longer questions on the chat window, and I guess we can stay on afterwards if you like, Dave. You can, if you want to kind of read and respond to individuals from the longer chat, but as we're the end of the allotted period, I think I'll kind of formally wrap up the formal part of the webinar. And thank you, Dave, very much for the excellent presentation, the excellent overview of obviously a lot of hard work from yourself and colleague students. A reminder to all the participants here, the next webinar is going to be in 2 weeks. James Burton's going to be talking about some of the observations from induced seismicity on the other side of the pond from the UK. So greatly looking forward to that. And thank you everyone for joining in today, and have a good weekend, good long weekend if you're from the US.
Thank you.
Thank you so much, David. So, David, I have a question about the pressure diffusion that we discussed as the last question. So you mentioned that the fracture network can play a role in pressure diffusion to the fault in some lateral distance from the stimulation volume. So is it possible to have this pressure diffusion along the fault? Like in disposal, we usually see some pressure reaches to the fault and then migrates down to the deep basement and causes large earthquakes. So maybe we can take a look at that as well if we assume that the fracture network in the stimulation zone can have a role for pressure migration to lateral distances. It can have a role to have some connection between the injection and deep basement.
Yeah, so I think that makes a lot of sense that you'd see pressure diffusion occurring along a fault. And in fact, I guess, the interpretation that I presented here, where we're saying these are large-scale fracture systems, possibly Rydell shear structures that formed as part of this fault system. Maybe you could think of those as being small faults if you wanted to. Maybe if you don't mind, I can just share once again,
Sure.
Very quickly. So one thing that's interesting is this area up here, which is kind of northeast of the treatment program here, the 4 wells. With 3D seismic data, we do actually see a fault which cuts right through this cluster of seismicity. The fault is closer to north-south than what these things are. So we're actually, and these things are displaced from the program, and we don't see a continuous set of microseismic events that connects this over to the well. So we actually interpret this as a damage zone around the fault. And the fault itself is much more conspicuous in the 3D seismic data than this one is. This one is extremely subtle. This one here is clearly mappable in 3D seismic. The fault itself was not activated during hydraulic fracturing, but I think we are seeing activity within the damage zone around the fault. So, and the damage zone could actually be sort of a more permeable zone around a fault that plays the role that you just described. So being kind of a permeable pathway that would connect fluid injection, you know, in a sedimentary layer like the Arbuckle group down into basement faulting.
Thank you.
While you're on this, I think Pierre-Francois Rowe is still on. Pierre-Francois was asking if Nadine considered aseismic slip as a potential triggering mechanism here, is the pressure diffusion.
Well, I think that this particular work emphasizes the pressure diffusion and the modeling that was done to look at the timing and relationships of these clusters with this fault. In my mind, the aseismic slip is still compatible with this. So, you know, there could be aseismic processes which are taking place in the reservoir level, but the key part of the story is the pressure diffusion that you're looking at here. That doesn't really answer the question, but really the focus of this work was on the pressure diffusion part.
Great.
Thank you.
So David, I have another question. So it's very interesting to me that you showed that most of these events are in shallower depths compared to the depth of the horizontal leg. So actually, that is something that modeling can confirm as well in the latest results that I'm doing for geomechanical modeling of this. So because of horizontal stress gradient, we see the migration of the hydraulic fracture upward, and then it reaches to some fault, and then it can justify the occurrence of events more in the overlying layer or in shallower depth compared to deeper formation, just because finding a very tough layer in the shallower depths may be very hard to just stop the height growth of the fracture and then cause the fracture to grow down in height. So, so I just wanted to add that it was very interesting from the modeling point of view as well.
I guess just from an observational side, I would caution that we certainly don't see events above the injection zone as a general rule. The 2 case studies that I showed here, you know, indicate that the rupture occurred above it. And because we weren't expecting that, that really caused us to dig a lot deeper into those specific cases. But I've got many other cases where induced seismicity seems to be nucleating below the injection zone. So I don't think that there's I can generalize. I can say that we have a couple of good cases, you know, that, you know, good examples where that does seem to be the case.
Dave, so Pat McClone was asking a question on chat as well about dynamic friction coefficients, the differences between the Wabamun and the Ireton. Any feel, do you have calibration or constraints on what the difference in friction coefficients might be between the different units?
Well, that's, I mean, we're just starting to collect that kind of data experimentally ourselves at the University of Calgary. So my response would just draw from the literature. So for example, the Coley and Zobak paper, which took samples from 3 shale plays in the US, they were seeing friction coefficients from 0.4 to 0.8. And the modeling work that Dimitri Garagash did as part of our Science Advances paper, he's actually seeing friction coefficients drop below 0.4 once he invokes this sort of flash heating in the carbonates. But we don't have any new data to add, new experimental data to add to that yet, but it's certainly something we're really interested in doing.
Great. And then there's one other here from I hope I'm pronouncing this correctly, Yasin Grigoras. I'm sure I didn't do a very good job pronouncing the name. Apologies for that. 2 questions though. Any particular reason why you use the rate and state model versus, say, the seismogenic index technique?
Well, we actually, the seismogenic index technique, we certainly do have the data that would allow us to do that, because we have both the injected volumes, good control on the injected volumes, as well as the seismicity rate. So we can calculate a number, the seismogenic index, pretty accurately. But maybe the question is referring to the triggering front, trying to use the triggering front and estimate the volume of the region which is impacted by that. I'm not sure that that approach necessarily informs the aseismic model that we're arguing for here, because based on the aseismic model, we expect that there's a deformation region which is not seismically detected. So that might sort of partly answer that question, but I do think that more could be done with a seismogenic index, but we've used rate and state in our work here.
Great.
And so, by the way, I've compiled all of the questions and comments from the chat, and I emailed an early version. Another question or comment just came in, so I'll send the 4 of you a new version.
Great. Well, thank you. Yeah, I've opened up the chat window now, so I can see all of them. And
oh, okay, good.
Yeah, it's just when I had it on full screen mode, I had to hunt for. I lost the little chat icon. So.
No problem. So, Madi, I don't know, is it possible can we unmute people that are still on in case there's questions people would.
Yes, we can unmute them. So anyone who wants to ask questions in person, please unmute and ask it. They can unmute themselves, I think. There is no limitation.
We have the top of Pat McClellan's head from Calgary.
Yeah. Yeah, I did have just a comment, Dave, because I noticed you had used the Trent Kaiser example of a bedding plane shear event, and given that I know that well because that's the figure I released, I just want to make the comment that that particular event is one of only 2 examples where there was a casing failure that resulted in a loss of integrity in a well that occurred several hundred meters above a Montney zone, and it did produce an earthquake that occurred simultaneously with when the event occurred and the leak occurred. So the earthquake was recorded on our national network. I don't know if Sean remembers that one, but this all happened about circa 2013 or so, and but it was the only one of its type that we saw that was so severe and disturbing because it was many hundreds of meters away from where we were injecting.
Yeah, thanks for that clarification, Pat. Yeah, I stand corrected. I didn't actually appreciate that event was connected to a measured earthquake. what I have right now in this area, and sort of the apparent lack of connection between many casing failure events and induced events is pretty anecdotal. They come from meetings and presentations and questions I've asked and everything. But so my understanding is that most of these casing failure events, no one can attach a specific induced earthquake to. But there are also timing limitations as well, because I'm not sure that people go back in and run a multi-caliper well log in these wells immediately following an induced event. So we don't know exactly when the casing deformation.
Oh, very much. And for example, a lot of those Fox Creek events, a case was put forward to get multi-finger caliper data in the wells closest to the activity, but it wasn't considered a priority at the time, and to my knowledge, it was never run. But I'd be most certain you'd see some deformations in pipe adjacent to big events.
Yeah. Okay.
Yeah, we had a magnitude 3.1 where actually, ironically, I think the event that Pat was referring to was about a 3 as well, if I remember, Pat.
Yes, it was. Yeah, it was exactly a 3.0, I think.
So we had a 3.1 in Oklahoma, and oddly enough, even though we had magnitude of completeness down to about below magnitude 1, other than a magnitude 3, but after the event, we couldn't get back into the well with guns. So
I'm just looking at a new question that was posted by Luigi Improta. I'm not sure if he's still online right now or not, but it is asking about, whether, all faults, can be detected using 3D seismic data, or whether the lack of detectability of these kind of fault structures, how that plays into the hazard analysis. This is quite speculative, but I'll go ahead and say it. We're seeing cases where we can map faults, and whereas the structures that are potentially seismogenic, that prove to be seismogenic in retrospect, are more subtle in the 3D seismic data. So one could possibly argue that the faults with more net displacement that are more easily detected in 3D seismic data, the bigger faults might actually be less prone to activation by virtue of having some kind of cementation or something that occurred, whereas faults that are more difficult to detect in 3D seismic might actually be more prone to be reactivated. So I'd be interested in anyone's views on that, but that's kind of a thought process that we're kind of working our way through right now. But I can sort of confirm that there are many cases where induced events are occurring on features that are difficult to discern even in high quality 3D seismic data.
from my side, I'd certainly echo that, Dave. It's especially in areas of strike slip, it's very difficult to sometimes actually image the feature. And unfortunately, one of the best ways to image it geophysically is to light it, use the induced seismicity to define it. Not good or satisfying from a pre-planning seismic mitigation point of view, but often we've, exactly as you described, kind of big events on something that only by going back and looking in detail at seismic sections have you been able to identify any signature with the faults.
Can I ask a question? It's follow-up of the seismogenic index question that I asked. If we were to do something with volumes, would you consider all the fluid types that are reported in frac progress, for example, or in IHS? Do you think some treatment types cause more seismicity than others? Because IHS has a lot of different treatment types and fluid types for each frac job. So I was wondering which types would you consider and which you would neglect?
Well, I have seen claims that you know, the fluid type, the rheology of the fluid, such as its viscosity, you know, could be quite important in terms of the tendency for fault reactivation to occur or not. I myself don't have any direct experience researching that question, but I think it would be, you know, certainly something which is worth investigating. I think it's a little bit hard to investigate because many of the events, if not all of the ones that that I've worked with, have been slickwater completion programs. So we don't really have enough data to assess that, but that could well be something which is worth looking into.
Thank you.
Okay. Well, if people are interested in contacting me directly offline, I'd be very happy to continue any of these conversations.
Okay, guys, any other questions? Please unmute yourself and ask.
Say, Dave, I thought I had to ask, I noticed in the mechanics cartoons at the start, you depicted injection zones, and oddly, you seem to have an induced fracture propagating horizontally, and I wondered, is there any significance to that, or was that just the graphic rendition of a vertical fracture?
Yeah, that's actually a really good point. That was just a graphic rendition of a vertical fracture. It was just intended to be a way to show schematically, you know, the horizontal extent of a hydraulic fracture. But yeah, it's a good point. It's maybe a little bit hard to show that properly in a schematic diagram like that.
Yeah. At the same time, there are some lines of evidence that at some of these events, and including that one I referred to earlier, actually must have been horizontal to intersect the number of wells that were deformed at one interface. So I, you know, and Sean's published on this in zones as well. I think, yeah, there are conditions under which we get some horizontal fractures along weak interfaces, and maybe that's the dominant fracture even at 2,000 meters depth.
Yeah.
I should say something about this because Mark Zovac and I wrote a kind of an extended abstract on this topic that you may have seen. In general, in certain parts of Western Canada where there's reverse faulting, you might actually have some horizontal hydrofracks, but we don't expect weak interfaces to, you know, bedding planes and so on to actually slip in normal or strike slip faulting cases, and you know, it's basically impossible unless the pore pressure is essentially lithostatic. But in Western Canada, the faulting regime becomes compressive enough further west that it's possible. In some places, maybe.
Very true. And the case I referred to is very close to our deformed belt. And you're right from a theoretical perspective. But the point is, we do find ourselves injecting well above the overburden pressure, and in many settings, the injection pressure on treatments gets very, very high. So it's not impossible to get it to injected pressures that are in excess of all three principal stresses.
I think that once you reach the minimum stress, that most of that pore pressure escapes off into the hydraulic fracture. You generally, you know, the general thinking is that you can't exceed the minimum stress except for that small net pressure difference.
I haven't seen the extended abstract. Where was that?
This is an SEG thing. I can send it to you.
Oh, I'd be interested for sure. Yeah.
So Pat, are you talking about the fracture breakdown pressure, like
no
at the initial time that you exceed, or just over?
No. This is yeah. You've gone well past that, pumping typically large treatments out of perforations.
So Dave, it kind of seems like the group here is getting a little bit aseismic going. It's time to wrap it up, and I know my coffee cup's empty. But thanks again for this. It's great.
Yeah.
Obviously generated a lot of interest. Appreciate with the round the world kind of visit that we had the opportunity to come to area. I think we're going to come back at least to BC, and Stu Venables is going to be doing one in a couple weeks.
Okay, great. Well, it was my pleasure, and thanks for the invitation.
Thank you so much, everybody. We had a great webinar.
Yeah,
Thanks.
thank you.
Great. Good seeing you, Pat. Thanks for the discussion. And it looks like our next presenter, James Verdon's on as well. So looking forward to that for
Okay.
sure.
Great. Okay. Take care.
Yeah.
All right.
Okay.
Thank you. Have a
Bye.
good day, guys.
Have a great one.
Thank you. Have a good day.